Hello, welcome back to episode 46, and today we're going to look into recursion, and specifically we're going to look at an implementation of map for array. So as we know, map is a thing that we get when something is a functor, and we know that an array is a functor, and if you don't know that yet, there's some videos. You can definitely just search my channel here for some videos on functor, and you'll find some stuff for that. But I want to talk about recursion because it's a very common pattern in functional programming. And I want to talk a little bit about why. This will also go with our whole imperative to functional transition. So if we look at a way that we might implement map for an array, we would be given some sort of a function, which is our mapper, which is going to take us from an A to a B, and then we would get some sort of an array. And then you could create a result variable here, and then iterate over the array for the length, and then for each one of those that you find, pass the actual item into this mapper function, and then take all of that and push it onto this result. So we're constantly mutating this result, which is why let here has to be a let rather than a const. Actually, that's not entirely true. But we're constantly mutating this. I left it as a let here rather than a const just for the idea that we're mutating something here. Not the pointer, so technically let works, but anyway. And then at the end, we're finally going to return result. So then if we call map and we pass x, a function from x to x plus 1, and an array of 1, 2, 3, then we get 2, 3, 4, just as we would expect. So this is one way to do it, but this is a very imperative way to do this. This is a very declarative way to do that. We're telling whatever runs this eventually that the way that it should deal with going through an array and doing stuff is to first instantiate a result array, then create this I variable, and then iterate through that, find the length of the array, do all of those things, and finally return the result of all of those computations. We're telling it how to do it. And with recursion, we're going to be a bit more explicit about that, or more declarative about it, rather than explicit actually. But and we're also not going to be mutating anything. And so let's see what that looks like. And this may look a little bit scary if you're not used to it, or you haven't seen our ellipsis or our spread or rest operator here. But what we've got is I'm going to call it RMap, just so that we don't have a collision of names here. But we're going to take a mapper, and we're going to take an array. So this is an array that we're just destructuring into the head, which is the first element of the array, and then a tail, which is an array containing the rest of the array. And then we're going to have another argument here for our accumulator. And if an accumulator is not provided, then it will just assume that it's an empty array. And what we're going to do is we're going to see if the head exists. So we're doing a kind of a truthy check here on the head. And if we have something in the head, then what we do is we're going to recursively call our RMap function here. We're going to continue passing through this mapper function, so that doesn't change. What do we pass to the array portion here? Well, we pass the tail, because we want the rest of the array. Well, then what's the accumulator? Well, the accumulator is just whatever's currently in the accumulator plus the result of calling our mapper function on h. And then if h is falsy, in other words, there's nothing else in the list, then we just return that accumulator. So we've got this thing where, in this case, it's we're kind of doing a pattern match kind of thing, but it's just on a Boolean because we don't really have great pattern matching here in JavaScript. But we're checking if the head exists. If the head exists, then that means we have something in the array, and so basically, if we were to run this, we would get the same thing: 2, 3, and then 4. So the way that would work is the first time when we pass 1, 2, 3 into this RMap function, the first time that it comes through, the 1 is our head, and then the tail is an array of 2, 3. And our accumulator will be empty array. So since our head is 1 here with our h, it's a truthy value. So we're going to recursively call map. And we're going to pass in our mapper function. So this thing stays the same regardless. We're going to pass the tail into it now. So the next time we call into our map, the head would be 2 and the tail would be an array of a single element, which is 3. We're going to create the accumulator the first time that we're doing this. The accumulator here is just an empty array, so that just kind of gets squashed. And then we're going to call the mapper function that we have here, x plus 1, on 1. So the first time that this ran through, if we didn't recursively call our map, if we just returned the accumulator comma mapper here, then what we would end up having is we would have a 2 that's returned because we would perform that mapper on the 1. But basically this is how you have it. The concepts of a recursive function, you're going to call the function again. One thing to always remember is that you for sure want to have a default case where you return whatever your accumulator is, because if you don't, then you have an infinite loop, which you probably don't want. That's probably unintended, and if you're running this in a browser, most browsers are going to realize that that's an infinite loop, and they'll actually throw an error for you. But some things to note. In here, we're being very declarative. We're saying that this thing has to be created. We've got to create this variable, and then we're going to constantly mutate it throughout as we're iterating through. We're also mutating this I value with our I++ here. So lots of mutation, lots of things happening here. Within this, everything is completely immutable. We're never modifying a value. We're updating new each time it goes through the stack. We're updating new. So that's an imperative view, and here is a more functional view. It just so happens to be a recursive function where everything's immutable, but it still matches up. Take a look at this, play around with it, see what you think about it. We'll probably revisit some recursion some more and dig into it maybe a little bit more here as we go on. Thanks for watching. This has been episode 46.